Now today we are going to discuss an important topic which is regarding the resistance, resistivity and conductivity. Now here we are talking about electricity. Okay, when the electricity passes through a conductor, it offers some kind of resistance. The conductor offers some kind of resistance to the flow of electric current. But we are going to understand it with the help of flow of water. Now this is a pipe, an ordinary geyser pipe that we had at home. Now this pipe, notice what happens is that water comes from one end and it leaves the other end. Now of course, as water flows through this pipe, the pipe offers some kind of resistance to the flow of water, very similar to the resistance offered by any kind of conductor to the flow of electricity. Now why does the pipe offer resistance? Because the pipe has its own surfaces, it has its own modulations inside the surface. Water strikes those atoms and molecules of the pipe, and of course because of which the resistance is offered to the flow of water, not very dissimilar to the resistance offered by a conductor to the flow of electricity, because the conductor itself would have some kind of atoms and molecules inside it. As electrons pass through, they will strike these atoms and molecules of the conductor, and the conductor would in turn offer some kind of resistance to the flow of these electrons. Okay, so what is the way to increase the resistance of this pipe? Now if I want to stop the flow of the current or stop the flow of water, what would I do? Right, see, our natural instinct is I would fold this pipe. What am I doing? I am trying to create a sort of constriction here. That is what would happen, right? This I am sure you must have done with your hose pipe at home several times. To stop the flow of water, what do? You try to create a constriction here. What does it mean by constriction? We are reducing the surface area, the cross-sectional area, not the surface area, but the cross-sectional area of the pipe, and that in turn would increase the resistance to the flow of the current. The same thing we can do in the case of conductor also. As we decrease the cross-sectional area of the conductor, the flow of the electrons decreases. The conductor starts offering more and more resistance. Now what's the other way to increase the resistance to the flow of this one? If I make this pipe longer and longer and longer, right, and imagine that before this pipe and after this pipe I have like free flow, okay, there is no resistance. Okay, then if I increase this length of, as I increase the length of this thin pipe, again I can increase the resistance offered to the flow of water in the case of pipe. And of course the same thing holds even in the case of a conductor, that as I increase the length of the conductor, I increase the resistance. Now this relationship is captured very nicely here with the help of a term known as resistivity. So we'll just now start writing the equations, because we have gotten a hang for it. Now R is typically what we say resistance. As we said, even in the case of pipe and in the case of conductor, resistance is inversely proportional to cross-sectional area. So as I increase the surface area, the electrons have more and more room to flow through, and because of which as the electrons have more and more room there available to flow through, the resistance offered to the flow of electrons decreases as I increase the area of this conductor, the cross-sectional area of this conductor. So resistance is inversely proportional to area. Now what is the other thing? As I increase the length of this conductor, okay, notice that these leads here, these wires, they have zero resistance. They are ideal wires. Okay, the same thing we said even in the case of our hose, our pipe here, that before and after this pipe I have very huge large pipes before and after the hose, and those pipes do not offer any resistance. Okay, so that's what we said even in the case of the pipe also. But in the case of this one, what we are saying is that in the case of conductor, what we are saying is that as I increase the length of this conductor, which has resistance, before the conductor these leads and after the conductor these leads, whatever is there offers no resistance at all. Okay, so these are ideal wires. What we say, these are ideal wires. So as I increase the length, I increase the resistance, and the resistance is directly proportional to the length of that conductor. Okay, so that was it, and we combine these two equations and we get R is proportional to L by A. Now we introduce a constant of proportionality. Okay, so what do we say? R is equal to rho L by A, and rho here is known as resistivity. Resistivity, it has the units of ohm meter. Okay, ohm meter. Okay, so we'll write that down. This is the resistivity. It is an intrinsic property of the material. The material, it offers certain amount of resistance to the depending upon the material, this rho would change, and because of that the even a unit area of the material would offer some kind of resistance to the flow of electric current. Okay, so that is about the resistivity. Now that is the first term, resistivity, that we are introducing. The second term is known as conductivity. It is noted by sigma, and that is equal to 1 upon the resistivity. Okay, very simple. So if I can also write R is equal to 1 upon sigma L by A. Okay, why? Because the resistivity, the conductivity is 1 upon the resistivity. So this is known as conductivity, and this is the resistivity. Okay, so that is the second important thing that we have learned here. Now the third thing that we will learn is how does the resistivity change with temperature. The resistivity typically increases with the temperature. Okay, and in absolutely terms, if you want to be very exact, we'll say that relative resistivity changes with relative, is directly proportional to relative temperature. Okay, and we will derive this equation in another class, but for the purposes of our discussions here, very roughly we can say that resistivity increases with temperature. So as I increase the temperature of the substance, this resistivity increases, because of which if the dimensions do not change, if the length and area do not change at all, even then the resistance of that substance would change, because this rho here, this rho term would actually increase, and that would cause the R term to actually increase. Okay, so those are the three things here. First is resistivity. Resistivity is the inherent property of the material, and that comes from this equation, proportionality constant. Second term is conductivity, that is inverse of resistivity. The third thing is that resistivity increases with the temperature. This equation, the rho L by A, this equation is very important, and you can expect questions on this equation in your exam. This equation is also known as Claude-Paulet equation. Okay, this is known as Claude-Paulet equation also. Okay, Claude-Paulet equation, and this equation is important. Questions will be asked, and how are the questions asked? If the length of the conductor is increased 2 times and its area is decreased 4 times, how would the resistance change? Would the resistance increase, decrease? What would happen? And then you have to use this this particular equation. Sometimes temperature related questions are also asked, and we will be solving such problems. Many are solved already on doorsteptutor.com. Practice the questions there, but we will also be solving some questions here. So subscribe to this channel if you want to understand how to solve numericals based on this particular equation. Okay, so that was about this equation. It is important equation. Learn it by heart, and I'm sure you will be able to solve the problems related to this equation very easily. Thank you.